In probability and statistics, students' t-distribution is any member of a family of continuous probability distributions that arises when estimating the mean of a normally distributed population in situations where the sample size is small and population standard deviation is unknown, developed by William Sealy Gosset, under the pseudonym Student. Whereas a normal distribution describes a full population, t-distributions describe samples drawn from a full population. Accordingly, the t-distribution for each sample size is different, and the larger the sample, the more the distribution resembles a normal distribution. The t-distribution plays a role in a number of widely used statistical analyses, including students' t-test for assessing the statistical significance of the difference between two sample means, the construction of confidence intervals for the difference between two population means, and in linear regression analysis. The student's t-distribution also arises in the Bayesian analysis of data from a normal family. If we take a sample of n observations from a normal distribution, then the t-distribution with degrees of freedom can be defined as the distribution of the location of the true mean, relative to the sample mean and divided by the sample standard deviation, after multiplying by the normalizing term. In this way, the t-distribution can be used to estimate how likely it is that the true mean lies in any given range. The t-distribution is symmetric and bell-shaped, like the normal distribution, but has heavier tails, meaning that it is more prone to producing values that fall far from its mean. This makes it useful for understanding the statistical behavior of certain types of ratios of random quantities, in which variation in the denominator is amplified and may produce outlying values when the denominator of the ratio falls close to zero. The student's t-distribution is a special case of the generalized hyperbolic distribution. History and etymology. In statistics, the t-distribution was first derived as a posterior distribution in 1876 by Helmert and Leroth. In the English language literature it takes its name from William Sealy Gosset's 1908 paper in Biometrica under the pseudonym Student. Gosset worked at the Guinness Brewery in Dublin, Ireland, and was interested in the problems of small samples. For example, the chemical properties of barley where sample sizes might be as low as 3. One version of the origin of the pseudonym is that Gosset's employer preferred staff to use pen names when publishing scientific papers instead of their real name, so he used the name Student to hide his identity. Another version is that Guinness did not want their competitors to know that they were using the t-test to test the quality of raw material. Gosset's paper refers to the distribution as the frequency distribution of standard deviations of samples drawn from a normal population. It became well known through the work of Ronald Fisher, who called the distribution student's distribution, and referred to the value as t. Definition. Probability density function. Student's t-distribution has the probability density function given by where is the number of degrees of freedom and is the gamma function. This may also be written as where b is the beta function. For even, for odd, the probability density function is symmetric. As the number of degrees of freedom grows, the t-distribution approaches the normal distribution with mean 0 and variance 1. The following images show the density of the t-distribution for increasing values of the normal distribution is shown as a blue line for comparison. Note that the t-distribution becomes closer to the normal distribution as increases. Cumulative distribution function. The cumulative distribution function can be written in terms of I, the regularized incomplete beta function, for t greater than 0, with other values would be obtained by symmetry. An alternative formula, valid for, is where 2f1 is a particular case of the hypergeometric function. Special cases. Certain values of given especially simple form. Distribution function. Density function. See Cauchy distribution. Distribution function. Density function. Density function. Density function. See normal distribution. How the t-distribution arises. Sampling distribution. Let x1, xn be the numbers observed in a sample from a continuously distributed population with expected value mu. The sample mean and sample variance are given by the resulting t-value is the t-distribution with n-1 degrees of freedom as the sampling distribution of the t-value when the samples consist of independent identically distributed observations from a normally distributed population. Thus, for inference purposes, t is a useful, pivotal quantity, in the case when the mean and variance are unknown population parameters, in the sense that the t-value has then a probability distribution that depends on neither mu nor sigma 2. Bayesian inference. In Bayesian statistics, a t-distribution arises as the marginal distribution of the unknown mean of a normal distribution, when the dependence on an unknown variance has been marginalized out, where D stands for the data, she, and I represents any other information that may have been used to create the model. The distribution is thus the compounding of the conditional distribution of mu given the data and sigma 2 with the marginal distribution of sigma 2 given the data, with n data points, if uninformative, or flat, location and scale priors and can be taken for mu and sigma 2. Then Bayes' theorem gives a normal distribution and a scaled inverse chi-squared distribution respectively, wherein the marginalization integral thus becomes this can be evaluated by substituting, where, giving so but the z integral is now a standard gamma integral, which evaluates to a constant. Leaving this as a form of the t-distribution with an explicit scaling and shifting that will be explored in more detail in a further section below. It can be related to the standardized t-distribution by the substitution. The derivation above has been presented for the case of uninformative priors for mu and sigma 2, but it will be apparent that any priors which lead to a normal distribution being compounded with a scaled inverse chi-squared distribution will lead to a t-distribution with scaling and shifting for p. Although the scaling parameter corresponding to S2, n above will then be influenced both by the prior information and the data, rather than just by the data as above. Characterization. As the distribution of a test statistics student's t-distribution with degrees of freedom can be defined as the distribution of the random variable t, with where z is a standard normal with expected value 0 and variance 1. V has a chi-squared distribution with degrees of freedom. Z and V are independent. A different distribution is defined as that of the random variable defined for a given constant mu. By this, random variable has a non-central t-distribution with non-centrality parameter mu. This distribution is important in studies of the power of students' t-test. Derivation. Suppose x1, xn are independent realizations of the normally distributed, random variable x, which has an expected value mu and variance sigma 2. Let be the sample mean, and be an unbiased estimate of the variance from the sample. It can be shown that the random variable has a chi-squared distribution with degrees of freedom. It is readily shown that the quantity is normally distributed with mean 0 and variance 1. Since the sample mean is normally distributed with mean mu and variance sigma 2, n. Moreover, it is possible to show that these two random variables are independent. Consequently, the pivotal quantity, which differs from z in that the exact standard deviation sigma is replaced by the random variable Sn, has a student's t-distribution as defined above. Notice that the unknown population variance sigma 2 does not appear in t, since it was in both the numerator and the denominator, so it cancelled. Gosset intuitively obtained the probability density function stated above, with equal to n-1, and Fisher proved it in 1925. The distribution of the test statistic, t, depends on, but not mu or sigma. The lack of dependence on mu and sigma is what makes the t-distribution important in both theory and practice. Properties. Moments. For the raw moments of the t-distribution are moments of order or higher do not exist. The term for k-even may be simplified using the properties of the gamma function to for a t-distribution with degrees of freedom. the expected value is 0, and its variance is if. The skewness is 0 if and the excess kurtosis is if. Relation to F distribution has an F distribution if y equals x2 and x tilde t has a student's t distribution. Monte Carlo sampling. There are various approaches to constructing random samples from the student's t distribution. The matter depends on whether the samples are required on a standalone basis, or are to be constructed by application of a quantile function to uniform samples, e.g., in the multidimensional applications basis of copular dependency. In the case of standalone sampling, an extension of the Boxmüller method and its polar form is easily deployed. It has the merit that it applies equally well to all real positive degrees of freedom, nu, while many other candidate methods fail if nu is close to 0. Integral of student's probability density function and p-value. The function A is the integral of student's probability density function, f between -t and t, for t0. It thus gives the probability that a value of t less than that calculated from observed data would occur by chance. Therefore, the function A can be used when testing whether the difference between the means of two sets of data is statistically significant, by calculating the corresponding value of t and the probability of its occurrence if the two sets of data were drawn from the same population. This is used in a variety of situations, particularly in t-tests. For the statistic t, with new degrees of freedom, A is the probability that t would be less than the observed value if the two means were the same. It can be easily calculated from the cumulative distribution function f nu of the t distribution, where x is the regularized incomplete beta function. For statistical hypothesis testing, this function is used to construct the p-value differential equation. The PDF of the t distribution is a solution to the following differential equation. Non-standardized student's t distribution. In terms of scaling parameter sigma, or sigma2, student's t distribution can be generalized to a 3-parameter location scale family, introducing a location parameter and a scale parameter through the relation, or this means that has a classic student's t distribution with degrees of freedom. The resulting non-standardized student's t distribution has a density defined by here, does not correspond to a standard deviation. It is not the standard deviation of the scale t distribution, which may not even exist, nor is it the standard deviation of the underlying normal distribution, which is unknown. Simply sets the overall scaling of the distribution. In the Bayesian derivation of the marginal distribution of an unknown normal mean above, as used here, corresponds to the quantity, where equivalently, the distribution can be written in terms of the square of this scale parameter. Other properties of this version of the distribution are: this distribution results from compounding a Gaussian distribution with mean and unknown variance, with an inverse gamma distribution placed over the variance with parameters n. In other words, the random variable x is assumed to have a Gaussian distribution with an unknown variance distributed as inverse gamma, and then the variance is marginalized out. The reason for the usefulness of this characterization is that the inverse gamma distribution is the conjugate prior distribution of the variance of a Gaussian distribution. As a result, the non-standardized student's t distribution arises naturally in many Bayesian inference problems. See below. The scaled inverse chi-squared distribution is exactly the same distribution as the inverse gamma distribution, but with a different parameterization, i.e., in terms of inverse scaling parameter lambda, and alternative parameterization in terms of an inverse scaling parameter, defined by the relation. Then the density is defined by other properties of this version of the distribution are: this distribution results from compounding a Gaussian distribution with mean and unknown precision, with a gamma distribution placed over the precision with parameters n. In other words, the random variable x is assumed to have a normal distribution with an unknown precision distributed as gamma, and then this is marginalized over the gamma distribution. Related distributions. Non-central t-distribution. The non-central t-distribution is a different way of generalizing the t-distribution to include a location parameter. Unlike the non-standardized t-distributions, the non-central distributions are not symmetric. Discrete students t-distribution. The discrete students t-distribution is defined by its probability mass function at R being proportional to here A, B, and K are parameters. This distribution arises from the construction of a system of discrete distributions similar to that of the Pearson distributions for continuous distributions. Further generalizations. We can generate student t-samples by taking the ratio of variables from the normal distribution and the square root of chi-squared distribution. If we use instead of the normal distribution, e.g., the Irwin-Hall, we obtain overall a symmetric four-parameter distribution, which includes the normal, the uniform, the triangular, the student t and the Cauchy distribution. This way it is e.g. also more flexible than some other symmetric generalizations of the Gaussian distribution.